Good afternoon. I'm going to talk about.
Don't worry about the mic. Don't worry about the mic anymore.
Oh, okay. So I'm going to talk about the intersection of big data with extreme scale computing, and that is the space where I work mostly. So I work in the GIS'13 group till recently. Now I am lead data scientist for the division. So some of these slides may not make big sense here, but I made this for extreme scale computing community to show what are some of the big data problems in spatial domain. So what this graphic essentially showing you is starting from 1970s to till today on 3 different axes, how the improvements in remote sensing technology is leading to big data in terms of volume, velocity, variety, etc. So for example, 1970s, we were dealing with a pixel of size 1 kilometer by 1 kilometer. And if you look at on spatial axis, so we are now dealing with sub-meter pixel resolution. That means each location, now instead of 1 pixel, you have 10 to the power of 6 pixels, right? So that is the volume we are dealing with. Similarly, on spectral, modest bands of 3 or 4, now hyperspectral 250 bands. And in temporal domain, so I started some 15 years back in India, so we used to wait till the next image comes after, let us say, 21 days, Landsat images. But now, at any given time, each day, you can have almost data from 10 different sensors. So there is improvement in all of these, leading to so-called VV, and there are several V's beyond what I listed here. So more concrete example, like let us say look at the tiling organization of MODIS data. So each MODIS tile, there are 460 tiles, and each tile is 4,800 by 4,800 locations, which is roughly 23 million locations in each tile at 250 meter resolution. And if you take that and translate to 1 meter resolution, so you are going from million to trillion, 1.5 trillion locations for the same data set, same spatial extents, right? So that is the complexity you are dealing with. And you have to process 460 tiles. If you, let us say, remove water tiles, still there are roughly 350 tiles you have to process to extract information. So what kind of stuff we are doing on these images? So here are a couple of examples that our research is focused on. Given an image, can you predict a certain visual category? Or given an example image, can you find in your collection of millions of images, similar images? Like for example, example here is a cooling tower from nuclear power plant. And if that is your exemplar image and your objective is to go and find similar or images which have similar features. On the bottom hand, this is a different kind of problem. If you look at those 3 images, the objects are same, right? Buildings, trees, roads, maybe water bodies. But if you look at those 3 images, the neighborhoods in those images are different. So for example, here, I don't know if you can see, each of these buildings have a car parked outside, right? And whereas here, there are no cars parked outside, but most of these buildings have swimming pools, right? Even the objects are same, but the spatial structure tells these are different neighborhoods, which can be related to different socioeconomic conditions. So we want to identify these neighborhoods. So we are also trying to identify change patterns. Here is an example of damaging pattern because of hailstorm damage. And as the time progressed, actually, all these fields got destroyed, and we want to identify those kind of damaging patterns. Here is another example, high resolution image where we want to identify, if you look at this building here, that entire building here got destroyed, and we want to identify those kind of changes. Here is another example. Can you infer, by monitoring, can you infer before the intent of someone constructing some kind of facility, right? So So for example, what China is constructing, looking at this time series image before they actually constructed a refinery or nuclear power plant, etc., based on the initial conditions. So here are some of the frameworks that we are developing. This is biomass monitoring framework, where objective is to identify changes like this. So this particular quadrant, top left quadrant, is showing one kind of change. So all over the years, it is corn, but suddenly we don't know what happened, right? Fallow. And here, corn, those fields are converted into soybean. And here is an interesting change. If you look at these two, there is no change. Corn, but if you look at the pattern, corn, soybean, so we are able to identify those kind of changes as well. These algorithms are computationally expensive. I will show a couple of examples. And here is another example. Here the objective is, given an image like this, can you label that entire image as a nuclear power plant or thermal power plant or something else? So here are a few examples. Right? Given a collection of images, the algorithm takes these images and assigns a visual category. Like these are airports, these are nuclear power plants, those are thermal power plants. So here is the overall framework. So we start with the raw images. We have almost, I think, outside of NASA and maybe Department of Defense, we have largest high-resolution image collection reaching about 0.5 petabyte. And we also have small images of, we collected for this particular testing scaling of these applications, we collected about 12 million images from the web. But if you look at web scale, actually, web scale is now billions of images. So what is the computational challenges in this framework? For example, the biomass change detection framework. So the challenge is to find the inverse of covariance matrix. So at any given location, right, out of that 23 million locations, each location is a time series. And the length of this covariance matrix is length of time series, right? So essentially, to represent this covariance matrix, you need order t square memory. And you have to invert this, this covariance matrix, and that is order n cube. But sometimes you get lucky. If you look at the structure of this matrix, this is a Topless matrix, meaning that if you look at these values here, these are repeated in the entire matrix. So as a result, I need to store only the first row in the memory. So which essentially, I require only order t memory and order t square algorithms to solve this kind of problems. Even that is not good enough, because you are talking about millions of locations. So we parallelized shared memory as well as distributed memory systems. And now we are looking at heterogeneous, because our Titan is now heterogeneous. One of the examples I presented is like identifying different neighborhoods in the image. And those algorithms are also computationally expensive, order n square ND. N is the size of this window you are looking at. So, and n is the number of training samples, and E is the dimensionality. And these images, because of the spatial resolution, we are looking at sub-meter resolution. Even at 1 square kilometer spatial extents, it takes about 27 hours. And we parallelize to get about reach for the same size data set for 2 hours. So in summary, what we have and what we are missing. If you look at HPC, certain things are very well defined. So for example, we have very well optimized linear algebra packages, right? And parallel IO libraries like NetCDF, ADIOS, etc. And bitmap indices, for example. If I go to my super leadership computing environment, this is given to you. But nobody gave me something similar to do something for spatial stuff, right? I have to start coding everything by ourselves. So there are no well-defined libraries to do spatial analytics. So that is one gap. I think when you go for extreme scale computing, we need libraries, well-matured libraries, in terms of machine learning, data mining, and geospatial analytics. With that, I conclude.
Great. Thank you.